So, so what we did last lesson is we introduced these motion equations, otherwise known as suvat equations. So suvat, S-U-V-A-T, they're the letters that represent displacement, initial velocity, final velocity, acceleration, and time. This only describes a situation in which something is moving at constant acceleration. So you can imagine it starting from a particular velocity and moving at a constant acceleration up to a new velocity. So the motion graph would look like this, and we've shaded it for, we'll get to the reasons why that is in a moment, but it'll be a straight line because it's constant acceleration. In other words, the rate at which the velocity is changing is constant, and so it'll be a straight line. So you can apply suvat equations to anything where the acceleration is constant, providing we have enough information about it, of course. For example, an object moving at 5 meters per second accelerates up to 20 meters per second over 3 seconds. What is its acceleration? Well, you use this equation at GCSE. We know it's just a change in velocity, or the increase in velocity divided by the time taken. You can work out the increase in velocity by the final velocity, take away the initial velocity, and then you divide it by the time taken. And so you would just do 20 minus 5, which is 15, and divide it by 3, and so you get the acceleration is equal to 5 meters per second squared for that question. Now, by rearranging it, you get it into the form that is usually quoted as the first motion equation in A-level physics. I've color coded them. It looks like I forgot to color code these ones down here, but in fact, let's just maybe correct that now. But I've color coded them just so we can see that we're using all the different variables in the equations. Apart from one, each equation is missing one variable. So the first one is missing the displacement, the second one is missing velocity, the third one is missing acceleration, the fourth one's missing time, and sometimes you have this fifth one, and that will be missing the initial velocity. This fifth one is often not quoted, but it's just a rearrangement. I think what they've done is they've combined equation 1 with equation 2. It looks, maybe, I'm not sure. Anyway, so you could, it's not really necessary to kind of work all those out, but I did show you how to derive some of them. So deriving the first one I just mentioned by rearranging our understanding of the definition of acceleration. The second one can be derived by looking at a graph, a velocity time graph, and remembering that the area underneath a velocity time graph will give you the displacement. So this is a trapezium, so we can not trapezium. Yes, no, not trapezium. I think it is. I don't know. Anyway, but it can, in any case, it's a triangle on top of a rectangle. The rectangle is going to be equal just to that height multiplied by that length, which would be ut. Then the triangle is going to be equal to. Made a mistake here. Look. That should be half. It is trapezium, yeah. I thought it was. Oh yes, it's trapezium on its side, of course. Yeah, yeah. So I should have written that because it's an area of a triangle, so it's going to be half of that. So it's going to be half times the velocity, final velocity v minus u, so which will give you that length there, and then multiplied by the base, which is t. And that's going to be, and then you can, what we did there is we took v minus u multiplied by t. Hang on, so that's going to be half a t squared. So by because we said v minus u is actually equal to at, but just by rearranging this equation up here. So then we can sub that into this bit here. In other words, writing at instead of v minus u. And then multiply it by the t, leaving half at squared. Therefore, altogether, the area is going to be equal to ut plus half at squared. That was how I did the second one. The third one is actually a little bit easier. The third one is just going to be the equal to the average velocity